Bismillahirrahmanirrahim. Welcome in class of real analysis. Hello dear students, I hope you are all keeping well. In today's lecture we will discuss the Euclidean spaces and the properties of norm. So firstly we discuss how can we define Euclidean space. For let k is a positive integer, then this set Rk, this is a set of all ordered k tuples. This is called k-dimensional Euclidean space, and it is defined as this is the space of k tuples. This is similarly as in case of R square, you define it as this is the set of all order pairs where x1 and x2 are the real numbers. Similarly, in the case of R3, you defined this is the set of triplets x1, x2, x3, where x1 and x1, x2 and x3, these are the real numbers. So actually here R square, R cube, or even R called the Euclidean spaces, but having the dimension 1, 2 and 3. So in more general, if we have a k-dimensional space such that it consists on k coordinates, or it consists on elements that are of k tuples, is called the Euclidean k-dimensional Euclidean space. Here x, which is of this form, this is called a point or a vector of Rk, where x1, x2 up to so on xk are the coordinates of x. This is similarly when in plane geometry you write p x1 y1, then x1 and y1 both are called the coordinates of point p. Similarly here x1, x2 up to so on xk, these are the coordinates of point x. In Rk we can define vector addition and scalar multiplication in such a way that x and y are the 2 points in Rk and alpha is a real number, and this is called scalar. Then their addition x plus y is given by the sum of the corresponding component x1 plus y1, x2 plus y2 up to so on xk plus yk. That is, we will add the corresponding components to obtain the sum of two vectors, and the scalar multiplication can be defined as simply multiply alpha with each coordinate, that is alpha x1 multiply alpha with x2, we have alpha x2 up to so on alpha xk. The zero element of Rk, sometimes called origin or the null vector, this is denoted by the bold letter O, and this is a vector all of whose coordinates are 0. That is the null vector is of this form. Further, you can note that the vector addition and the scalar multiplication defined in Rk satisfied the commutative, associative and distributive laws that make Rk into a vector space over the field R. I hope you are familiar with all of these terms and you have taught all of these terms in linear algebra course. Next, we define inner product scale, or it is also called scalar product or also called dot product in Rk. For all x and y belong to Rk, the inner product is simply or defined as x dot y. In other textbook you can see that the inner product of two vectors x and y is denoted by these angle brackets, although this notation is not given in Walter Rudin textbook. Walter Rudin denote the inner product of two vectors just by this notation, and it is given by the product of sum of product of corresponding components of both vectors. That is, we will multiply x1 with y1, x2 with y2, up to so on xk with yk, and then summing. We have the summation form of inner product. Summation I is equal to 1 to k xi yi. Norm or length of vectors in Rk. For all x belong to Rk, its norm is denoted by this symbol x absolute, or it is also called magnitude of the vector, and can be defined as, this is the square root of the dot product, and further it can be written as this is the sum of squares of the components of x. If we have a vector x1 vector x whose components are x1, x2, x3 up to so on xk, then the magnitude of this vector is simply the sum of square of these components. For example, if I have a vector x 1, 2, 3 belong to R cube, then its norm is simply given by 1 square plus 2 square plus 3 square, which is equal to 1 plus 4 plus 9, that is square root 14. Next, we define some important properties of norm. Suppose x, y, z are the three vectors in Rk. Alpha is a real number. Then the first property say that the norm of x is always greater than or equal to 0. That is, norm cannot be negative because it is magnitude, and magnitude cannot be negative. The norm is equal to 0 if and only if the vector itself 0. The norm of alpha x is the next one is the absolute value, the norm of x dot y is less than or equal to the product of their norm. Now, E is the triangular inequality, and F1 is x minus z norm less than or equal to x minus y plus y minus z. The first part is the norm is non-negative. It is clear from the definition of the norm, as for any x belong to Rk, we can define the norm as, this is the square root of sum of squares, and sum of square is always positive, always non-negative. So this shows that norm is greater than or equal to 0. In the B part, we have to show that norm is 0 if and only if the vector itself is 0. Suppose the norm is 0, where our x is x1, x2 up to on xk. As the norm can be defined as the square root of the sum of square, this is equal to 0. As you know, the square root is, if the square root is 0, it means the number inside the square root, these are 0. This sum is 0. If the sum of square is 0, it means every term is itself 0. It means x1 square is equal to 0, x2 square is equal to 0, xk square is equal to 0. The square of the term is 0, it means the number itself is 0. And this shows that this each coordinated 0 implies x is equal to 0. And now if you reverse the sign, you can obtain the result. The next one is the norm of the scalar product alpha into x is less than scalar multiplication is less than is equal to absolute value of alpha into x norm. Let x is k tuple vector, and multiply x with alpha, we have alpha x1, alpha x2 plus 1 alpha xk. But using the definition of norm, we can write it as alpha x1 square, alpha x2 square up to so on alpha xk square. By taking alpha square as a common, we have x1 square plus x2 square up to so on xk square. By separating the square root we have and convert this sum into summation form. As alpha can be negative and positive both, so we can write it as absolute value of alpha, and this is the definition of norm of x. The next one is the norm of x into y is less than or equal to product of their separate norm. Let x is equal to this vector and y is this. Firstly, we can define the product, scalar product x into y, as this is the sum of product of corresponding components, and the norm of x is square root of sum of square, and similarly the norm of y is square root of sum of y squares. Similarly, if you take the norm of x dot y as x dot y, this is a scalar number. So in this case, the norm or the absolute value have the same meaning. So this is equal to the absolute value of this sum. Now, by using the Schwarz inequality that we discussed in our previous lecture, the Schwarz inequality says that the square of sum of product is always less than or equal to product of sum of squares. Or this can be written as, if you take a square root on both sides, the absolute value of sum of product is always less than or equal to the product of square root of sum of squares. As this is the definition of x dot y absolute, and this is equal to norm of x, and this is equal to norm of y. Hence, we have the required inequality. The next one is triangular inequality. To prove triangular inequality, we use the result as norm of x square. This is equal to x into x. That is the dot product. So by using this result, we can write as norm of x plus y square equal to x plus y dot x plus y. Now, taking the dot product, we have x into x, x into y, y into x, y into y. As x into y is equal to y into x, and further x into x dot x is equal to norm of x square, and y dot y is equal to norm of y square. As dot product is commutative, so x dot y and y dot x both are equal, and we can write it as 2 times x dot y. In the above property, we have shown that x absolute of x dot y, norm of x dot y is less than or equal to norm of x into norm of y. As dot product can be negative here, so when you take the absolute, then x dot y is less than or equal to its absolute value, and further this is less than or equal to x absolute into y absolute. So the sum of these three terms is less than or equal to sum of these three terms. This is the square root of x norm plus y norm, and by taking square root on both sides, we have norm of x plus y is less than or equal to norm of x plus norm of y. To prove the f part, this is the norm of x minus z less than or equal to norm of x minus y plus norm of y minus z. We just replace x is equal to x minus y and y is equal to y minus z in above part in the triangular inequality. The triangular inequality was x plus y less than or equal to norm of x plus norm of y. So in this inequality, replace x is equal to x minus y, this becomes x minus y, and replace y is equal to y minus z, this becomes y minus z, less than or equal to x minus y plus y minus z. Cancelling out y, we have norm of x minus z less than or equal to norm of x minus y plus norm of y minus z. So in today's lecture, we have discussed Euclidean spaces and the properties of norm. I hope today discussion is helpful for you, and now you have a clear understanding about Euclidean spaces. In the next lecture, inshallah, we will start our exercise. So see you in the next lecture. Take care. Allah Hafiz.